I think I've told you all roughly what Lindstrom's theorem is. First order logic is strongest logic with nice properties. And I'll explain what logic is, what nice properties are, how you prove this, all that stuff later. First, though, I'm going to prove a fun thing, which the proof I will draw before I say what I'm proving. Error. That is the proof. The statement is, there are more sets of natural numbers than there are natural numbers. So here's the idea. I take the natural numbers. For me, natural numbers include 0, because there's no elephants in this room. Neil, shut up. There are elephants in this room. I have a lot of them. I don't know who wrote this first, actually, but there, in one of his books, Galileo actually mentions that there's as many natural numbers as there are even natural numbers, which seems rather weird. But it makes sense, right? 0 goes to 0, 1 goes to 2, 2 goes to 4, n goes to 2n, and I pair every natural number with an even natural number, and vice versa. So there are as many even numbers as there are natural numbers. There are also as many prime numbers as there are natural numbers, as many odd numbers as there are natural numbers, as many, I don't know, numbers greater than 37 as there are natural numbers. It's part of this whole tradition that sort of infinity is the same everywhere. All infinite sets are the same. Turns out that's not quite true. Here's the idea. Fun piece of math notation that I'm not really sure strictly how it came about. I'm hoping this is because it stands for power set, but it probably doesn't. This weird, so first of all, that's just the symbol for natural numbers. This weird symbol P, that is pronounced power set, which I think is where it comes from, but for some reason, I'm not actually sure that's true. That might come from somewhere else, that might be a coincidence. This weird thing is just a set of all sets of natural numbers. This is a very big set, right? It contains the set of even numbers, the set of odd numbers, the set containing 1, the set containing 37, the set containing all prime numbers, which are not the number of cows currently living in a city in Wisconsin. It contains a lot of numbers. It's very infinite. So the question is this bigger than the natural numbers? First of all, it's obviously at least as big as the natural numbers, right? There are obviously at least as many sets of natural numbers as there are natural numbers. Because given a natural number, I get a board that I forgot to erase. Sorry.
I don't think that's what you get when you consider the natural numbers.
Apparently it is, though. It's really weird. The natural numbers have been changing. I think someone eliminated all their quantifiers.
Shut up.
Me. So given a natural number, which I call n, I put curly braces around it, and I get a set of natural numbers. A rather boring set of natural numbers, right? It only has one natural number. But I get a set of natural numbers. So there's at least as many sets of natural numbers as there are natural numbers. But there's no reason to believe there's strictly more, right? I mean, it seemed like there might be more natural numbers than even numbers. That turned out to be false, because you can actually pair them up. It seemed like there might be more natural numbers than prime numbers, because there certainly seem to be very few prime numbers. But that still didn't pan out, because you can map them. 0 goes to 2, 1 goes to 3, and so forth. So there's a fairly decent chance that if we're clever enough, we can give every set of natural numbers a natural number, and we can sort of go backwards. And we can show that there are as many natural numbers as sets of natural numbers, which would be kind of cool, and really say that all infinite sets are the same. Unfortunately, it doesn't quite work like that. So, reality is good. Like everything good in mathematics, it proceeds by supposing that it's false and then exploding the universe. So we start by assuming that I can count sets of natural numbers. So first of all, what the hell does this mean? This isn't a formal talk, so I'm not really going to do any formal definitions, but basically it means this. I have a list. It goes to infinity. On the left, I have natural numbers. On the right, I have sets of natural numbers. So maybe it's containing 4 and 7. The set containing every even number. The empty set. the set of all natural numbers, and so forth. And my rule is that every set of natural numbers should appear here somewhere. If I can do this, that's obviously a sign that there's as many natural numbers as there are sets, right? Because I've given every set a number. So this is the idea. This is getting a little closer to that picture over there. Sets are irritating. Sets don't have a lot of geometry, and geometry makes proofs easy. So what I'm going to do is I'm going to rewrite this. The set containing 4 and 7 is a sequence. It goes like this. Oops, sorry, one more second. First 4 zeros, then a 1. Then 2 more zeros, and another 1. And then zeros from then on out. Where did I get this? It's a way of coding the set. So my rule is, I want to be able to, from this, tell stuff about this set. The only two things in this set are 4 and 7. So the only two parts of the sequence that get 1s are the 4th digit in and the 7th digit in. No, that's not quite true. There's a 0th digit right here, because 0 is a natural number. Unfortunately, this is tradition, and so I can't actually say 4th digit. But I number the digits in the sequence 1, 2, 3, 4. Sorry, 0. Epic fail. 0, 1, 2, 3, 4. 0, 1, 2, and 3 all have to have zeros, right? Because none of those numbers are in my set. 4 gets a 1. 5 and 6 get zeros. 7 gets a 1. Then everything else gets zeros. This thing, well, that is a similar sequence. Starts out with a 1 because 0 is in my set. Then a 0 because 1 is not in my set. Then a 1 because 2 is. Then a 0 because 3 isn't. And it just keeps alternating. So the set of even numbers looks sort of like an alternating sequence. And then the empty set, that's just all zeros, right? Nothing's ever put in it. And all natural numbers, everything's a 1. Now, I can actually give some meaning to this picture. So, again, suppose I'm able to count sets of natural numbers. Then what I can do, what I'm really doing, is counting sequences of zeros and ones, right? Because every set is a sequence, really. So I write them up. So maybe 0, 0, 1, 0, 1, 0, 0. More stuff is my first set. My second something might be the even numbers. My third set might be really stupid or something. My fourth set might not contain any numbers. And so forth. And ideally these should line up, which they don't, so I'm going to fix that a little. Right? Over here, I have the natural numbers they correspond to. Now I do something fun. This is where having good handwriting would actually help me significantly. I take the diagonal sequence, right? I've listed these things in a sort of table. I can go down the diagonal and get another sequence of natural numbers, right? Not just natural numbers, but zeros and ones. In this case, it's something like 0, 0, 1, 0, and then I don't know what it does after that because I haven't written it out yet, right? Now, I define something new. In general, whenever we can't think of letters, we shaking? What? No, that's that.
No.
What? Okay. Sorry. So, in general, whenever I somehow forget the entire English alphabet, I'll put a twiddle over whatever letter I just used. This is a standard practice in logic. For some reason, logicians cannot keep track of the entire English alphabet at once.
It's large.
Yeah. 26 is a big number. I generally don't deal with numbers that aren't 0, 1, or infinity. 2 actually. 2 actually. I deal with 2 occasionally, but not 3 or 26. So, what do I do here? I take D, the diagonal, and I change every single number. So it looks something like 1, 1, 0, 1.